Okay, so I thought I'd make a video today, which is from day 5 of the past paper program. It's question 7, and I thought I'd do this as a bit of a teaser of what we could do if the program does start up again, if we get enough people replying to my email about wanting the program to start again. Cool. So it's question 7. We've got these cards with Rory, and he's taking them without replacement, and that without replacement part here is really important. Because that tells us that as we take out a card, the probability is going to change for the next card that we take. Cool, so we're trying to show about the probability for part I, that if you take 3 cards and add up the numbers on those cards, that you get 11. And so when you think about it, you've only got 3s and 4s as the numbers that you can add up. So the only way to get 11 from that is to maybe have a 3 and then 2 4s, or possibly a 4, a 3, then a 4, or maybe even 2 4s and a 3. There's no other ways to make those numbers add up to make 11. And what you need to do is work out the probability that goes with each of these. So it's kind of like partitioning, like we do for combinations or permutations, and then working out the probability of each and then adding it up. And we know we should get a half altogether. So you could set up a tree if you wanted to. So for example here, we're either going to get a 3 or a 4 on our cards. Because there are 4 cards with 3s on it, initially it's 4/10 chance for that 3, which means there's 6/10 chance for the 4. And we could keep doing this down our tree. I'm actually just going to go down one branch here, actually this branch here, the 3 4 4 branch. Because if we do it for one branch, we can just use the same answer for the other 2 branches. So, other 2 paths through, I should say. So, I'm over here. So, I've got a 3, and I'm looking at what's the probability of getting a 4. There's still 6 4s left in the pack, but now there's 9 cards left. And for the 3, there's now 3 3s left. And if I look down here, getting a 4 again, well, I've lost a 4 because I took one out on this go here. So now I'm down to 5 4s, and now there's 8 cards left. So for this pun here, the probability of getting a 3, then a 4, then a 4 is going to be 4/10 times 6/9 times 5/8. Okay. Now you would need to repeat this, or if you did it the long way, you'd need to repeat it for getting a 4, a 3, then a 4, or a 4, a 4, or a 3. Actually, what's going to end up happening when you do that is you're going to actually end up with the same product after you've multiplied across the whole tree. I'll show you what I mean. So let's say I filled out the 4 4 3 one. So we know that the probability of getting a 4 on the first go is 6/10. The next go is going to be 5/9 because there's one less card and there's one less 4. And then when we go to the 3, there's still going to be 4 of those left because we haven't taken any 3s yet out of 8. So for this one here, this one here, 4 4 3, I'm going to end up with 6/10 times 5/9 times 4/8. And if you look at this one and this one here, you can see you've got 4 times 6 times 5 along the numerators and 10 times 9 times 8 along the denominators. Here you've got 6 times 5 times 4, which is the same product as those numerators, and 10 times 9 times 8, which is the same product as denominators. Okay, so basically because you're just finding different combinations of the same kind of outcomes, I suppose, the probabilities each time are going to be the same, and you'll just end up with 3 of them. So your final probability here is going to be 3 lots of this, any of them that you want to choose. So 6/10 times 5/9 times 4/8, like that. And when you work that all out, you'll get a half. Okay, so then for part 2, they want you to draw up a probability distribution table for the sums of all the 3 cards. So a probability distribution table looks like this, where you have your outcomes. In this case here, along here, you're going to have the different sums that are possible from the 3 cards. And then down here, you're going to have the probability of getting that sum. So probably at the random variable x equals that particular one there. Oops, it's not coming out very well. I'm not sure about this pen. X equals x in there. Yeah. So, we've got to think of what the possible sums are So we could have all 3 cards being 3s, so the lowest sum is 9, or we could have all 3 cards being 4s, so the highest sum is 12. So then we've got these other 2 in between, so 10 and 11. Now from part 1, we already showed, or we can just take the answer from part 1, that the probability of getting 11 is a half. So actually all you have to do now is work out 2 more, let's say 12 and 9, and then what you can do is, because you know the probabilities of all the outcomes have to add to 1, if you work out the probability of 12 and the probability of 9, you can just subtract away to get the probability of 10. Probably the easiest way to do it. The probability of getting a 9 means you get the card for the 3 on it, for all of it. So that's going to be 4/10 the first time to get a 3 on it, then 3/9 the second time, and then 2/8. So all I'm doing is that whole sampling with replacement. So that's the probability of a sum of 9. And if you multiply that across, you get 1/30. So you can add that to your table. If you want to get a sum of 12 across the cards, that means getting a 4 each time. So there's at the beginning there's 6 cards with a 4 in it, and then that becomes 5 out of the 9 cards with a 4 in it, and then 4 out of the 9 cards with a 4 in it. So the probability of getting a sum of 12 is 1/6, and that should be an 8 there, sorry. Okay, so we can add 1/6 to our table there, and then if we just add those all up on our calculator using the ABC button for our fractions, and then take that's 7/10 when we add it up. So if we take that away from 1, we're going to get 3/10 as the probability of 10 there. And we're done. So I thought what I'd do is I'll show you the other way to do it, which is to use combinations. So we're looking at using how many ways we can choose the cards to get our probability. And remember how that works, if you want to use it, is that you have to think of a fraction. And on the denominator of the fraction is all the ways that you can choose the 3 cards. So given you've got 10 cards initially, and you're choosing 3 of them, you'd have 10C3 on the denominator of the fraction. So that's all the ways that you can choose 3 cards from 10. On the numerator, let's say we're looking at this one here, so we want the sum to be 9. That means we want all 3 cards to be 3s. We've got 4 to choose from, so we'd be doing 4C3 there. And just for completeness, I'm going to say 6C0. Oh, I can't see that 6. One sec. I'm going to say 6C0 here just so you can see. So I'm multiplying those 2 there. And I'm saying of the 4 cards that are 3s, I want to choose 3 of them. At the same time, from the 6 cards that are 4s, I want to choose none of them, so 0 of them. So that's all the ways that I can choose 3 cards that are 3s. And if you work that out on your calculator, you'll end up with 1/30 as well. Okay, and for part 3 and 4, you have to show 2 events are either independent or they're exclusive. So there's just a couple of rules for that, which is that if 2 events, if 2 events A and B are independent, then the rule you're going to use is that the probability of A times the probability of B, that equals the probability of A and B, or A intersection B. That's the rule for independence. For 2 events to be exclusive, so if A and B are exclusive, or we say mutually exclusive, if I can spell it, then the probability of A and B actually equals 0, or actually more better, equals the empty set. Okay, so there are no, there's no intersection for the 2 events A and B. So basically they can't happen at the same time. Okay, that makes them exclusive. So those are your 2 rules there. And it's really easy to get them confused, especially in a test, to remember which one's which. So I'm not too sure how to help you with that, but I think exclusive, maybe if you start with exclusive, 2 events being exclusive means they can't happen at the same time, and that should help you remember the rule that is that the intersection equals 0, and then from that I guess you can say by elimination, therefore the other rule that you're memorising in your head, which is that the probability of A times the probability of B equals the intersection, must be the independence rule. Okay, Anyway, in this case here, so R is the sum of the numbers on the three cards is 11. And so let's do that. So the probability of R, the sum of the three cards, we know that's a half, because that was part 1. The sum, an event S is the number on the first card taken as a 3. So a 3 on first card. So the 3 on the first card, oops, it's not really running well at all, is going to be 4/10, right? So that's what it is. There's 4 cards with 3s on it. There's 10 cards initially, and so that's fine. So those are our two probabilities, which over here would be the probability of A and the probability of B. So the probability of R, that'd be the probability of A, and this is like the probability of B. So when we multiply those two things together, so probability of R times the probability of 3 on first card, that equals 4/20 or 1/5. What we've got to do now is work out what's the probability that we have both happen at the same time, so the intersection, so A and B. So we'd need to go back to our tree and have a look at how that would happen. And we know from before there's the only way to get a sum of 11 if the first number is a 3 is to have 3, then 4, then 4. Okay, so the probability of the first number being a 3 and the sum of everything being 11 is going to be the outcome there, which was 4/10 times 6/9 times 5/8. That was just going along the tree that we had before. And if we work that out, and we get 1/6. Okay, so that's the probability of both, getting a sum of 11 and the first number being the 3. 1/6 is not the same as 1/5. So for two events to be independent, then if I take the product of the individual probabilities, it's supposed to be the same as the probability of both of those events happening at the same time. So those do not equal each other, so therefore they're not independent. Okay, so that's the independence part for part 3. So then for part 4, because we have worked out the intersection between the two events to be 1/6, so we've shown that they can happen at the same time there. This means that the events can't be exclusive, because if they were exclusive, the probability of A and B would have to equal 0, but in this case we've shown that it equals 1/6. So therefore, because this doesn't equal 0, the events are not exclusive.